Welcome to Alchemy Wizard. I'm Tom. Today I want to talk about a summation of my research on using lasers to create nanoparticles, colloidal nanoparticles. Now, originally I wanted to see if we could melt material with they call laser ablation. That's where you take a high power laser, you focus it on the metal, and it melts the metal and then creates the colloidals from the water melting, from the metals being released from there into the water and cooling into colloidal nanoparticles. And laser ablation is very well documented. The only problem with laser ablation is you need a really potent laser, something that my budget does not allow. And so I wanted to see, well, maybe 4 laser pointers focused, on a spot in the beaker could create some kind of colloidal. I've fathomed at least we'd be able to do it with maybe zinc and magnesium, because those metals have a very low melting point. Well, what I discovered was I really couldn't melt the zinc or the magnesium. Magnesium showed little signs that there was something going on there, but I'm not sure we really melted very much material. But I was able to create colloidals, which was really stumped me. And I contacted my chemist, and we talked about it, and we couldn't figure out. The weight on the scale showed that we lost material. The microscope showed we had colloidals in here. This right here is 14 karat gold used with the laser that you're seeing here, which is actually one of my best results that I got from the metals that I tried. And so something weird was happening, and we fathomed, and it's just a theory, that the laser light, the photons from the laser light are exciting the outer electron in the element of these atoms, and it's got so much energy in it that it has to leave the atom. And once it leaves the atom, that atom is removed from the metal because now it has a charge, and it goes into the liquid. And because the liquid is already floating, swimming with electrons, because we're bombarding it with the laser, those electrons are then reattracted to the metal, the piece of metal floating in the water, and it becomes neutrally charged, creates a nanoparticle. And then they clump together. These little atoms clump together into nanoparticle sizes. What those sizes are, I have no idea. I'm speculating they're kind of large. They might be over 60 nanometers, maybe as much as 100 nanometers, especially in the case of gold. But that's all kind of up in the air. Without an electron microscope, without a spectrum analyzer, the results are just what we see from what we can tell infer from the nature of things. We're losing material off the metal, so we know the metal's going somewhere. We see the increase in nanoparticles in the laser microscope, so make a guess there. Now, it hasn't been fully successful, and the reason I actually went into this method wasn't only just to explore it, was because I needed a stable form of vanadium for my forever mix that I make. This clear sort of stuff here is a combination of all different kinds of colloidals: platinum, gold, silver, magnesium, copper, vanadium. There's a whole bunch of them in there. So the reason for that was vanadium. Whether I did it with plasma arc or I created it with low voltage electrolysis, I could not get a stable vanadium. Within a couple days, the vanadium just unraveled itself. I said, let's try the laser idea. So I investigated, created the top to hold the lasers. It took a while to do that, and I did magnesium first, and I had tentative good results with magnesium. Magnesium is also a metal that is tough to stabilize with a colloidal. I can only create a few parts per million colloidal magnesium with low voltage electrolysis. I can get more with plasma arc magnesium, but over 60 days it starts to unravel itself, sometimes sooner. So magnesium laser magnesium could was a partial success. Yes, it seems to be very stable, and though the yields on the laser process are quite low in comparison, to plasma arc or even low voltage electrolysis, it takes 10 to 12 hours of subjecting the metal to the laser to get about a 10 or 12 parts per million solution, if it's possible. Zinc, I cannot get any colloidals out of zinc at all. That's a metal that seems to fail with laser. I am going to revisit zinc again. Molybdenum is another metal that failed, that I tested it on. No matter how much I did, I could not get colloidals from molybdenum. And hey, that's actually a good thing if you think about it, because if I'm creating colloidals from some metals, but I can't create it from other metals, something is going on here. And so that is, what I'm trying to accomplish with the laser stuff, besides being really cool. Maybe I can find, this would be another alternative way for people to make colloidals without having to put any, other chemicals in there. With low voltage electrolysis, you need to use sodium citrate and not with silver, but with some of the metals. With gold, ruby red gold, there's a chemical process going on there, so that is not a pure thing. Plasma arc gold is extremely pure, but it's inaccessible for a lot of people because of the dangers involved. Lasers might, making colloidals from lasers may be a good alternative for people who want a more pure colloidal substance. But it's all still experimental. It's still research, and I'm just sharing with you the things that I'm learning as I'm learning it, and some of the stuff may not be right, and I may have to reevaluate my theories on it, in which case I'm going to let you know in a future video. But anyway, that is the update on the laser stuff that I'm working on, and I'm going to have more research into the lasers. Next is going to be the red lasers. I want to experiment with red lasers because they may be more powerful than green, or the metals may respond better to red lasers than they do with the green lasers. In the link section will be all of the playlist of all of the laser stuff if you want to go back and review it, where I go into much more detail about what I think is happening with the lasers. So, I'm Alchemy Wizard. I'm Tom. You made it to the end. You got your cool.